Welcome to Linear Algebra. We're going to start the course with a brief introduction to Rn. We're going to use this structure throughout the semester, so we want to get a good foundation with it. Before we dive right into Rn, though, let's make sure we understand R. R is the set of all real numbers. And by the way, we use this symbol here to represent the set of all real numbers. It's the letter R, but it's written in a blackboard bold typeface. We call it blackboard bold because it's a way that we can make a letter bold, but in a way that's easy to write on a blackboard. Okay? Now, the set of all real numbers is pretty much anything you would think of as a real number. So as some examples, real numbers include positive integers like 2 and 3 and 7, and negative integers, -1, -17, includes 0. It also includes all rational numbers. Rational number is any number that can be represented as a fraction. So 2/17, 42 57ths, okay? But also all irrational numbers. Irrational numbers are all numbers that cannot be represented by a fraction. So numbers like pi and e and square root of 2. All of these are real numbers. Just about anything that you would normally think of as a number is a real number. Just about the only thing that is not a real number is an imaginary number, and anything involving an imaginary number. That's kind of the classic case. So I is not a real number. By I mean the square root of -1. Okay. Also complex numbers like 2 plus 3 times I. Okay. If it involves that imaginary number, it's not a real number. We geometrically represent the set of all real numbers with a number line. So 0, 1, 2, 3, 4, -1, -2, -3, -4. Okay, so a number like pi, which is in the set of all real numbers, this symbol here, it's a Greek letter epsilon, and it means that this is in this set, this collection of stuff, okay? So pi is one element in the set of real numbers. So pi is in the set of real numbers, so we could represent it on the number line. We know pi is about 3.14, so that would be right about here, okay? There's pi. But one real number all by itself is a little bit boring. Often in real life, we want to compare sets of real numbers. We want to look at relationships between multiple real numbers. For example, you might be interested in how some quantity changes over time. The first quantity is a real number, the time is a real number, and so you're looking at two real numbers and their relationship between them. Okay, so often one real number isn't enough. So we will look at all ordered pairs of real numbers. We call this R2. And in set builder notation, we write it as the set of all ordered pairs, x and y, such that x and y are both real numbers. Okay, x and y are both in the set of real numbers. Okay, so this is set builder notation. Sometimes instead of a colon, you will see a vertical line here. It means exactly the same thing. You would read this as the set of all of this that meet this condition. And we're within curly braces. Those curly braces say we're dealing with a set. Okay. So yeah, it's the set of all ordered pairs. And by the way, we're using variables x and y here, but there's nothing magical about x and y. I could use maybe t and x if I'm emphasizing time as one of my variables, right? Or a lot of times we will use subscripts if we want to use the same letter. All of these mean the same thing. It's just slightly different ways to represent it. And geometrically, since now we have two real numbers, we're going to need two number lines. Okay, one for our first variable and one for our second variable, our second set of real numbers. Okay, and so if I have a point that is in R2, for example, I could have 3 comma negative 2. That is an ordered pair that is in the set of all ordered pairs in R2. So I'd go 1, 2, 3 on the X. I'd go negative 2 on the Y. And there we go. There's the point there. Okay, so far so good. This should seem pretty familiar so far, even if the exact symbols we are using are a little bit new. But we can continue this. We've looked at looking at one real number at a time, looking at the set R. We've looked at looking at R2, that's all sets of ordered pairs of real numbers, all two real numbers. What if we throw in another real number? So we're looking at all ordered triples of real numbers. We've already used variables x and y. And the next natural choice would be z, x, y, z. So it's a set of all ordered triples, x, y, z, such that x and y and z are all real numbers. And just like before, there's nothing special or magical about x, y, z. So we could represent this with other variables if we want, such as x1, x2, and x3. Or maybe we want to relate an xy position and see how it changes with time. Okay, so how do we represent this graphically though? Well, with R, we looked at a number line. When we went to R2, we needed two number lines that were perpendicular to each other. So with R3, we're going to add a third number line perpendicular to the first two. We want to be a little bit careful here because we want to preserve some orientations. Okay, so let's start by considering R2. And I'm just going to focus on the positive part of the number line. So there's X. There's Y, and it will just help us keep track of our orientation. If we counted Y positive this way, for example, some of the rules that we're used to with the geometry of the space would be just a little different. So we want to make sure we preserve that orientation to keep the rules as familiar as possible. Okay? I want you to imagine this lying flat on a piece of paper. So the way we usually illustrate three-dimensional space, we start with the coordinate plane, R2, and we imagine laying it down flat. So my X will stay about the same. I'm going to lay that Y-axis down flat. Okay, and so now you could imagine we have a flat piece of paper. okay, lying flat on the desk. And so what we're going to do is the third axis we're going to add, we're going to draw it straight up. And this will be our z-axis, okay? And then we're going to do one more thing. Our x and y axes, our y-axis, our positive y-axis, it's kind of facing away from us, isn't it? We were going to take this whole plane and we're going to rotate it so that the positive part of the axes are front and center for each of the axes, okay? So if we rotate it in the plane, if we rotate it counterclockwise 90 degrees, what we are going to get is how we usually draw our three-dimensional space. Okay, so we have this becomes our y-axis because we've rotated it 90 degrees. Our x-axis rotates until it's over here. And this is our z-axis. And that way the positive portion of all the axes are front and center. Okay. Notice when drawing this, it does get a little busy if you were to draw the full axes all the way out. Okay. It just starts looking a little busy. And that's before we've even added anything else to this visualization. There's no points, there's no graphs, nothing. That's just the coordinate axes, okay? So to keep it a little less busy, we usually only draw the positive portions. And I've drawn little arrows here to kind of emphasize we do have those negative portions, but really when we draw this, we usually just draw positive portions kind of like this. X, Y, Z. Okay? And we just understand they're all orthogonal to each other. Now, drawing in 3D, it can be a little tricky because unlike with two-dimensional space, unlike drawing our coordinate plane in R2, what we did up here, that was pretty straightforward because we were drawing a two-dimensional representation of our space onto a two-dimensional object, onto a piece of paper, or in this case, onto a screen. Okay? With R3, it's a little trickier because we have three-dimensional space, but we're trying to cram it in to a two-dimensional surface. And so that's going to make it a little awkward to sketch graphically in R3. It's a little bit easier on a computer where you have freedom to rotate and it can automatically animate different angles. Okay, but on paper, this is usually how we represent the three axes. On a computer where you could rotate, it may not, and it doesn't have to always have this same orientation because you could move it around and interact with it a little bit more. Okay? But let me just plot a point for you just so you could see where it's what we're dealing with here. So let's plot the points 1, 2, 3 in R3. So that means positive 1 on the x, positive 2 on the y, positive 3 on the z. So I'm going to go 1 on the x, 2 on the y, 3 on the z. And to help me out, I'm going to draw some dotted lines just to help me keep perspective here. Oops, if I can draw them straight. There we go. Okay, and so this point right here is the point 1, 2, 3. I'm 1 on the x-axis, and we can see that with the dotted line. I'm 2 on the y-axis, and I'm up 3 on the z-axis. Okay, that's the point. Notice if I erase those lines, it would be really hard with what we have here to understand what we're dealing with here. Okay, to be able to see that we're dealing with exactly the point 1, 2, 3, and not some other point that looks similar, right? Going back to R2 for a moment, we know that the axes in R2, they divide the space here into 4 regions, 4 quadrants. Similarly, for R3, the axes divide the 3-dimensional space into 8 regions, which we call octants. Now, let me just illustrate real quick. And here, just to make the octants a little easier to visualize, I will draw the negative portion of the axes. So the first octant, and the most important octant, is the octant that you're looking right at. It's the octant where the x and the y and the z axes are all positive. Okay, so this octant right here, that's octant 1. We're not going to bother learning the numbers for the other octants, but no, there's 8 of them. So there's this one where x, y, and z are all positive. Then the one back here where the x is negative and the y and z are positive. There's the top left front corner here where the y is negative and x and z are positive. Then there's the top left back. And then down here, the front right bottom. And then the back right bottom. Front left bottom. And then back here, back left bottom. So there's 8 total, okay? 8 octants. Furthermore, if you look at pairs of axes, we get different planes. So right here, the plane that the x and y axes go through, that's called the xy plane. The plane where the y and z axes go through, that's the yz plane. And the plane where the x and the z axes go through is the xz plane. And we could keep on going, right? So we've done R3, we could do R4. All ordered sets of 4 real numbers. So the first 3 variables are x, y, and z, but we run out of variables, right? There's no variable after z. So we actually go the other direction. We pick the variable before x, which is w. So it's a set of all ordered sets of 4 real numbers, okay? And just as before, and especially once we start getting to R4, we can use subscripts instead. And so I don't have to write all of them out. Sometimes we just write any of those x's with a subscript for any I 1 to 4 is a real number. Okay. Note, though, that once we get to four-dimensional space, there's no easy way to represent it. There's no easy way to visualize it geometrically. So a lot of the same geometric ideas still apply. We're going to learn that we still have a distance formula for four-dimensional space, but we can't visualize this space easily. There's not an easy, natural way to visualize it. And then continuing, you could generalize this to Rn, where n could be any number. Okay, 1, 2, 3, 4, 5, 17, 306. It just means we have n real numbers. And especially once we get past 4, we usually just use subscripts to indicate our variables. So x1, x2, all the way to xn, the nth real number, where all those xi's are real numbers. Okay? This ordered set of real numbers, we call it an ordered n-tuple. It's just n ordered real numbers. Okay, and again, generally for large enough n or greater, there's no way to visualize this set. But for any number of n from R1, we usually don't write the 1, but from R1 to R2 all the way to any value of n, a lot of them have the same properties. The properties are very similar. And so we just want to familiarize ourselves with these sets of real numbers.